Not race, it's a culture. Yes. Advice. Your student from 104 never do their homework. Because when you join a CCA, it's almost like a family you're joining. We have to raise you up well. Yeah? So like your PM, your form teacher, is one person who will take care of you, make sure you grow up well. Your CCA is the place you're going to be with for 4 years, right? In fact, you think about it, your PM will stay with you for 2 years. But your usually you try to stay 2 years. So from JH1 to 2. Then JH3 to 4 you get another PM. But for your CCA teacher, we stay with you for 4 years, some of you 6 years. So how you all grow up matters a lot to us. And so some CCA teachers have asked for subject teachers to let us know if anything goes wrong. Basketball is not there. Make sure you do your work. Okay, today we're going to yes and here. I don't understand, Mr. Amma is still here. I don't understand, like, is he now a PM of another class? Oh, okay, so a bit hard for the responsibility. It's okay, but thankfully it's still your LA teacher. I think that's very important. I'll share a little bit about my attire. So today I'm dressed in batik because at least in Southeast Asian countries, especially go to Indonesia, you will see a lot of men dressed in batik. Batik, I think, is an amalgamation of a lot of cultures, from Asian patterns to Malay patterns. And I wear this because I think it represents the culture I came from. My grandpa is Peranakan, so Peranakan I think is more like a culture than a race. We call it a culture because really Chinese, Indians, Malays from different parts of the world, when they migrate to the Southeast Asian countries, it's a mixing pot of different cultures. So if you look at Peranakan foods, it's very Malay, very Chinese at the same time. You look at a curry from a Peranakan culture, there's Asian, there's Chinese influence, there's Malay influence, maybe even a little bit of Indian influence, all the different spices all together. So I really like this attire. For those of you that don't have ethnic wear, okay, if you want to get something reasonable, not too expensive, you can go to either Little India, Chinatown, or Arab Street. Surprisingly, it's not too expensive. Yeah. So for example, I've seen like nice cheongsams or maybe those kabayas going for like $15. Yeah. So it doesn't go to the cost of, I used to think like as a student that it goes up to the cost of like $80 plus. But not mine. If you go Little India basement and Mustafa, in fact you can find a lot of different attires. You can even find the batik attire for around $15 or $10 even. Okay? So it depends on your comfort range or how much you want. Then you just get one, like myself, I wear once every year. So in total I've worn this 6 times. So 6 years already. People say it looks brand new because it's like brand new. I've only worn it 6 times. This is 6 years. But I wear it more often. It's very hot. Okay, today we are going to, so I'm going to see how much I can do. I think I will go through first. I'll close the chapter first. Whatever time I have, then I'll go through RB. If I don't have time, that means you have more time to complete your RB. But I think hope by today, you should be able to complete both sides of the worksheet. Next week, on Monday, I'd like to bring you into the lab. I'm going to teach you how to use the microscope. Okay? Yeah. This is my specialty, okay? How to use a microscope.
What are we going to be looking at?
Okay, so we are going to be looking at number 1. We are going to be looking at an animal cell, but I'm going to give you a particular specimen. I don't know if you all know what this is, so I'm going to give you an ovary to look at.
I don't know. Where do you get that from?
It's about a baby inside. Oh.
Samuel, that's not where babies develop. Babies develop inside the womb of the mom, not the ovaries. Yeah? Yes? Oh, sorry, yes, Isabel? How do I see the ovary? Okay, all of the specimens we provide you, I know when you think of an ovary or maybe a body part, it's like one organ, right? So normally how slides are prepared is that they are sliced very thinly and then they are put onto individual glass slides so that you can see almost through them. Isaac? No lah, I just buy it online. Okay, I think you all have got it all mixed up. I didn't even prepare the slides. Okay, these are professionally prepared. So you can literally, sorry? Oh, no. It's not human ovaries. Yeah? If I'm not wrong, they are rabbit or rat. Okay, so normally what happens is that you go online, then there's an online catalog, then you choose what slides you want, then you can get. Okay? Then other than that, you will be looking at a lead. Okay? So if you are able to pick up the skills well, and I pass you, like you can show me, you can achieve and find a very clear image for both. If you do it fast, and I clear you, and I say you pass, now you're certified, a very good microscope user, then I allow you to start looking at other things. You want to plug your own hair and put underneath also can. Okay? But only after I clear you of these two. Because if you cannot do the basics, I cannot trust that you can use it well for any other things. Okay, so that's next Monday. Okay, today we're going to close up the chapter. There are only a few more parts to this chapter. May I get you open your textbook? Okay, can I get you to go to page 24 and 25 today? page 24 and 25. Today we're going to learn about how temperature affects movement. First and foremost, before we begin, let's do a quick recap of the energies you learned before in school. Have you learned before this word, kinetic energy?
Yes.
Okay. And when you talk about kinetic energy, really you're talking about movement. How much movement energy do you have? And, thank you. So, Xavier has already picked up to summarize the first slide. Okay? When you talk about kinetic energy, two things affect kinetic energy. For example, number one, if I have two objects, one of them of a bigger mass, if I were to throw this to your face, okay, so this represents how fast it's going up. The arrow length represents the speed. Here I have a ball. Okay, usually it's B lesson. It's a ball with very, very big mass versus this one with smaller mass. Which one has more kinetic energy if I throw it at the same speed? Okay, number one, number one, mass affects kinetic energy. The bigger the mass, the more kinetic energy there will be. So if I were to take two balls, one bigger, one smaller, throw at the same speed in your face, you're going to feel a lot more, you're going to get a lot more energy within your face with this one. Okay, I pause a while. So Xavier and Isaac, Xavier? Only in a vacuum, in nothing, they will drop at the same time. It shouldn't. Okay, but that's a totally different topic altogether. It's a totally different topic altogether. But to sum up, if I were to quickly reply you, it would be that regardless of you will observe, okay, only if there is air resistance, then the heavier one will be able to fall faster. But that is the fastest reply we can do for now. Okay, then we go to Isaac. Okay, will weight be a factor? If we talk about weight, then we go back to what weight is. Weight is nothing more than how much force is being exerted on the mass. Usually things with greater weight has greater mass. So I would say it does affect, but it's not weight directly that affects, it is the mass that affects. Okay, if both of them have the same mass, so I throw both, same mass, same speed, and nothing is different, you will feel the same impact. Then Tristan? Oh sorry, Zen. Air resistance. I mean, assuming you throw in the same place, then air resistance is the same. So imagine both the same size, same mass, same speed. Yeah. Oh, okay. Are you saying that this also has the same mass? Oh, both same mass but different size. Okay. They would have the same kinetic energy, but to explain the next part will be a different topic. Has to do a little bit of pressure. If something is smaller, same amount of kinetic energy, I think you will feel this a little bit more painful. Yeah? It's like a bullet. Yeah, when you look at a bullet, it's really small. Okay, because there's a lot of pressure. Okay, last question, yes. Yeah, what Xavier was saying just now. Yeah, so as I was saying earlier on, this only happens in a vacuum if there's no air resistance. It happens because the amount of gravity that they both experience, right? The gravitational force pulling on them will be the same. Yes, but if you give enough distance, they will eventually reach the same speed. But very hard to explain without going to the whole topic of physics. Okay? Okay, next. However, example, if I have two balls of the same mass, so now we have two small ones, but one of them I throw at high speed, one at lower speed. Which one will have a higher kinetic energy? Okay, this one will have a higher kinetic energy compared to the one with lower speed. So two things I would like to recap with you from your primary school. How fast something goes and how much mass there are affects how much kinetic energy there will be. It's as good as if I were to take a bullet, I take one bullet, I just throw, I just use my hands to throw, right? Nothing's going to happen to it. Load it into a gun, fire it at very high speeds, the impact, the amount of kinetic energy is much higher. Okay, so that's a quick recap. The units for energy, I don't know if you were taught units in primary school, but the units is joules. Okay, but today we're going to focus on something else. I will require your iPad. Yes. Okay. Okay, I've written down a question posed by Isaac, which we will make sure we come back to her. Isaac asks, how do particles gain kinetic energy? From solids, all the best. From solids, Joshua gone already, From solids, liquids to gas. How do they even gain the kinetic energy to begin with? Okay, when you're in this simulation, this is what it should look like. Is anyone not scared? Actually, that's how kinetic energy can be transferred. When you bump into each other. Like imagine like a pool table. You know, a pool table when you wet, right? One ball can pass kinetic energy to another. Okay, I'm going to show the same simulation on the screen so I can direct you a little bit on what to do before you go crazy about this. Yes, you can. Okay, may I get everyone now? You pay attention to me, okay, I will give you time to play and go crazy. But now, let's learn. Can everyone press reset? Press the reset button. Press ready? Okay, after you press reset, press stop. Pause it. Okay? Okay, no, Xavier, no. Reset and stop. Okay, then now look to the screen. Let me direct you on what you can try. Okay, before you start. Okay, so hands off your iPad. Yeah, okay. Okay, let's look at the screen now. This simulation is meant to show you what's happening on a very, very small scale. When you heat things up. Okay, I say hands off your iPad up. When you heat things up, what are you really doing? You are supplying whatever you're heating up with a special kind of energy called thermal energy. You heard before? Yeah? But the interesting thing is, when you supply objects, liquids, gases with thermal energy, this thermal energy is converted to another form of energy. When the particle receives it, yes, it's converted to a form of energy that causes movement, kinetic energy, which is what this simulation is for. Later on, I'd like you to try a few things. Number one, don't try yet. Don't try yet. Let's watch what's up. So be very cute, her hands is just there, proving to me she's not doing anything. Okay, so when you press start, this is what you see. I would like you later on to try this. You add more thermal energy. Observe what happens to the particles as you add more thermal energy. Okay? Later on, also remove thermal energy and observe what happens. Okay, I'm going to reset. So that's number one. So number one, I would like you to do this. Add or remove thermal energy. Number two, I would like you to do this. I would like you to max out the thermal energy. Give it as much as possible. Okay? After that, I would like you to add more particles and see what happens. What do I mean by that? So I mean this, you will stop. Okay? I would like you later on, sorry, you start, you can add, max out the thermal energy. Then, I want you in the empty spaces, go and add more particles. And I want you to observe what happens as you add more and more and more particles. Is that okay? So two things I would like you to try. Once you've done both things, then you can start knocking yourself out. Okay, you may begin. Please try these two activities now.
Okay.
Xavier? Yes. No. When you add the more energy, the day the sun dies, all the suns in the world die, all the stars in the world, in the universe die, that will be the day when everything stops. Earth is moving because of the sun. Oh, they remove it. Seriously, every time I let you all do a simulation, you all discover a new function and you know. Oh, it says there you go. Oh, click to remove. Yeah, never read instruction.
Oh my god.
You can try. Yeah. Yes, it Is it not? I think I'm not read enough to be able to answer it. Yeah, you know every system you go. Okay, a minute more for you to enjoy yourselves. I need to understand what you're so happy about. Tara, you are a simple man. Simplest of things thrill you. Very good, very good. Okay, let's pause. Okay. I do need you to take a break now, so that you can play a second simulation. Okay. So can you take a pause? If not, we'll never hit the second simulation. Okay. Can I get you to stop arranging the particles in a solid state and stop packing as much as you can inside? I know all your tricks already. Okay. Please put your iPad face down. You can leave it up if you are taking notes. Okay? Maybe I'm serious. I need so that we can try a second simulation. Okay? Okay, so you've tried a few things. Let's have a look how we summarize. Number one, when I start this simulation, you observe. If you look at the top left hand corner, you can see there's a bar. It's telling you the redder something is, the more kinetic energy the particle has. Yeah? The faster it's moving. Observe how are the particles transferring kinetic energy to each other? Yeah, when they hit or bump into each other, that's how they transfer kinetic energy. Okay, and next, there's one way temperature, kinetic energy can be transferred. They bump into each other. And you have observed by now, if you add thermal energy, let's say there's a fire source nearby, you see that more of the particles are very, very red with high kinetic energy, right? What do you observe about the temperature when I added thermal energy? Increase, right? What happens now when I start adding, I'm going to pause it. What happens, and I'm sure you all have tried this earlier on, when you start adding particles? It starts to lose, make sure you use the words correctly, the temperature starts to drop. Notice? But why? Why is the temperature dropping when I add more particles? Because what, Rashmika? Okay. There are more particles now to Maybe it's the word you're trying to say share. Because yeah, I only gave this much thermal energy to this space, right? But if I add more and more particles, now all these particles need to share more of the thermal energy added earlier on. Yeah? And if you notice, the temperature starts to drop. Okay, let's restart the whole thing up. Let's play. You see that overall now, no single particle is extremely very red. They kind of distributed the kinetic energy quite evenly across. So I'd like to redefine temperature for all of you. I think to all of you, temperature is about how hot something is. But to a physicist, when they say the word temperature, then, okay, when we look at the word temperature, what physicists define temperature as is the average kinetic energy per particle in the system. What does that mean? It means, if I want to calculate it out, it is, let's take the total kinetic energy divided by the total number of particles. That's what temperature really is. And that's why if you have more particles with the same amount of kinetic energy, the temperature drops. Because actually what your thermometer is measuring is, on average, how much thermal energy is all the particles sharing with each other. That's what temperature really is. It's just an average of the amount of thermal energy shared among a certain amount of particles. So if you look at your textbook, I believe you should be able to see the equation. May I get you to highlight the equation? What temperature is? Yes. Okay, good question. Do plants have kinetic energy? Actually, remember, all states of matter have kinetic energy. Just that some have more than others. Solids have kinetic energy, but just so little that they can only vibrate about fixed position, their particles. Gases have the most. That's why they can move so fast and far apart. Yes?
Is that why when you apply heat or maybe like ice,
Yes.
water, then like more
Yeah. So when you convert one state to another, solid, liquid to gas, when you supply thermal energy, the particles start to move faster, they bump into each other more. That's how they change state. Okay? So in your textbook, we define what temperature is. Temperature is nothing more than the average amount of kinetic energy in the system. It means to say, whatever thermal energy is supplied in that box, you have to divide it among and share it among all the particles there. That's what temperature really is. Add more particles, the temperature will drop because now you have to share the thermal energy with more people. Sorry, not people, more particles. Well, let's try an exercise, checkpoint 2, before we go to the next simulation for today. As said earlier on, temperature equals average kinetic energy. So let's try. You write down A or B in the blanks on page 25. If object A and B have same mass, but A has higher temperature, which one has a higher average kinetic energy? This question actually is just testing you on the definition of temperature. Temperature equals average kinetic energy. So which one has a higher kinetic energy? Sorry, which one has a higher temperature? That is to find the one below. Yeah, you can either use object A or object B to fill in these blanks to answer these questions.
So the number of particles is the same
the same number of particles. Yes, I did.
Let's just say two objects have the same weight and they're like the same thing. Does it get the same particles or they go to A minus one particles? Amount of particles.
Oh. I think in the chemistry sense of it, you can assume they may be the same element. If they have the same mass. Yes, it's solid state. Yeah. Anything not moving, and you don't see move doesn't mean it's not kinetic energy. Just like your table. Sorry? Oh yeah, I guess light doesn't have kinetic energy. Okay, so let's look at first part. If object A and B have the same mass, that means same number of particles, but object A has a higher temperature, which object has a higher average kinetic energy? Considering that, temperature, the definition of temperature is average kinetic energy. So actually they are telling you the answer already. A. If A has a higher temperature, that means on average, the particles have higher kinetic energy on average. Which one will have a total kinetic energy that's higher? Also A. Because if they have the same number of particles, if this is the same for both A and B, that means the only reason why temperature is higher is because the total would have been higher. So A also. Let's look at B, part 2. If A and B have the same temperature, but A has more particles, which object has a higher average kinetic energy? It's a trick question. They already said that both A and B have the same temperature. Temperature is the average kinetic energy. So that means both A and B have the same average kinetic energy because they have the same temperature. The second part is the challenging one. One of them has more particles, but they have same temperature. Yes. Okay, maybe I need to remove this. To answer the first question, I was saying that if you compare A and B, if A has a higher temperature, and considering that they both have the same number of particles, so both A and B have the same number of particles, right? But A has a higher temperature. So the only way A could have had a higher temperature is if this one is higher. So that's what I'm saying. But I think I drew a wrong arrow. Yeah? So if this goes up, then this will go up also. Okay, and the answer is A. Okay, but why? Let's put it in diagram form. Imagine I have two boxes. I have two boxes here. One of them has more particles than the other. But on average, they have the same temperature. They have the same amount of kinetic energy. So, you see all these arrows over here? These arrows are trying to show you that if you, on average, each particle has around the same kinetic energy, almost moving same speed. So you look at this box over here. More particles, but moving the same speed as the particles here. But this object has less particles. So which one has in total more kinetic energy? Yeah, actually it is A. Because although all the particles are moving at the same speed, if you were to add up everybody's kinetic energy together, actually there's a lot more kinetic energy in this box. Okay? That's why A will be the answer. So that's the first property today that we are investigating. How temperature is affected by the amount of kinetic energy supplied. We will end off this topic with diffusion. Okay, another phenomenon we're learning today. I'd like you now to scan this particular QR code. Okay, wait. I learned my lesson. Hold on up.
No, sir.
Let me teach you how to use it first, then you scan it. Haha. Okay, teachers can also learn. It's different, huh? In this simulation that you will receive, I'd like you to try this. Imagine now you have a drop of liquid dye. And when you add this liquid dye into the water, this is what I'd like you to observe. I'd like you to try a few things. Number one, I'd like you to test it at low temperature. This, by the way, is water. Okay? I'd like you to shift it to low temperature, and I'd like you to add a drop of dye. Sorry, remove slow motion also. Okay? Observe what happens when you let the dye down, when you drop the dye in. After that, reset the whole process, and then shift it to a high temperature, and do exactly the same thing, and see what happens. Okay? That's all I'd like you to try. Anything else? You try after these two things. Okay? Goodness. Okay, there you go. Knock yourself out. Yeah. Yeah, that's how they spread. Hey, follow me. Tap and then see what happens, let it go. Not keep tapping. Yeah, when you tap, let the die go, and then see what happens. Don't keep tapping different places. Okay? Now I'd like you to let me know what happens when you increase the temperature. Have you tried the two things I've asked you to try? After that, you can knock yourself out and find other things to do. Okay. Okay. Now let's look to the screen. Everyone, please take a pause. Put your iPads down. or hands up in the air, or hands on your pens. Okay, something to write down later. Let's begin with low temperature. Okay, now listen to some observations from the ground. Yeah. Number one, when I add a drop of dye into the water, what do you observe happen to that drop of concentrated dye? It kind of disperses. They kind of separate. I don't know what you think. They kind of get mixed around. Sylvia? The same thing that happens when I release you for recess. Thank you. That's a very good example. Yeah? The same thing that happens. How might I put that in words? Well, number one, it moves from a region where it's high concentration to a region where there is low concentration. What is your lesson after this? B. Okay. Next. What if I increase the temperature? So let's talk around. What do you observe to be the difference when I max out the temperature? Ready? Okay, what the? I didn't even see happen. Okay, let's open. Okay, ready and pop. Okay. Rashmika, let's sum it up. Same thing. Same thing as in it spreads out from high concentration to low concentration. Except that at high temperatures, it spreads out faster. Oh, okay. So here I ask, when you stir, is this what's happening? Actually, when you stir, you are helping to spread, but not in this same way. Notice in this way you change it by temperature. Yeah. I'd like to introduce a new word to you today, but may not be new to you. The word is called diffusion. Okay?
Big science word that they use in sci-fi films.
Diffusion describes the process where liquid or gas spreads out from a region of high concentration to low concentration, which is what you observe for the dye. And when you increase temperature, actually diffusion occurs faster. So I don't want you to use the word spread out anymore from now onwards, now that you know the word diffusion. Okay? So later when I say lesson end, you all will diffuse to your B lesson. Okay, but this is a bad example because you are not liquid, you are not gas. Okay? Huh? Yeah, you are a mixture. Oh yes, you are going one specific spot. Okay? I think that's roughly where I may end today soon. Okay, to sum up today's lesson, diffusion is the movement of liquid or gas particles from a region of high to low concentration. And temperature definitely affects. At high temperature, it will spread out faster, or diffusion will occur faster. So over here, there are two images, one of hot water, one cold water. In cold water, the diffusion takes place at a much slower rate. For yourself, before you go off today, I'd like you to fill in some blanks on page 27 of your textbook. Okay, 26, you can skip it. It's exactly the same as 27. So go to page 27. We're going to try to explain what's happening. Okay, this is before you go off. Okay, those of you that are in your ethnic wear, you need to change for B, you probably need more time. You can take a photo of this and you can complete this at home. For those of you that cannot see or you want to take your time to write it down slowly, you can also take a photo to fill in your textbook. Okay, we'll use it. This is how we can describe diffusion happening. I will not go anymore. I'll not progress anymore today. Okay, thank you. But now that I've completed almost the end of the chapter, I'd like you to complete also page 2 for the next lesson. Our next lesson is on Yes, but that one we're doing microscope. Then after that it's Tuesday. So I'd like you to complete RE 8.1 by next Tuesday. Okay, so I swap this around. Teresa, I erase yours, okay? Okay, so by next Tuesday, I'd like you to complete RE 8.1. Okay, complete all. So usually and then anything in between, right? Just mix around. So usually how you call what is keyword, right? Teacher holding the textbook highlight. Then the English mix is up to you. Go and change. Okay, those in anywhere, need more time to change, go and change first. Yeah, so for yourself, for this section over here, you want to show how the dark blue balls are spreading out over time. 27, right? Oh yeah, they named it wrongly, yeah? Oh yeah, page 27. Pages are off. You can understand, can you? Those are fur balls. If it's on TikTok or Instagram, right, I will complain you to Mr. Jeffrey. Send one photo. No, wait, take photo of teachers send to each other. I've got even more advanced shops. Right, it's true.
Yeah, you were doing.
You can try, but I've seen students Okay, when you use the word heat, right, you use it the way like a verb. Heat up. Okay? So there's no more heat. You can't say there's more heat, there's more thermal energy. Yeah. Because the water particles have more thermal, more kinetic energy, they will bump into the dye more, then it's very hot. Okay, that's all. Please stand by for your PE lessons. Thank you, class. Diffusion 06. You're dancing today. Hey, up there, push up. Hey, push up. 5 up there. 5 up, push up. Yes, I'm doing it.
Go, faster.